Let me just go over a remaining small remaining topic in differentiation. That is nothing complicated. So it's just a matter of notation actually. After that, we'll discuss higher order derivatives, so successive differentiation, which is also a comparatively small topic for us, although more can be done in that. And then we'll move on to integration. So this notation that I'm talking about is normally you have a function y is equal to f of x, and then we write its derivative y dash, right? This is just notation for derivative of y with respect to x. Another notation for this is f dash of x. Now we know that this y dash or dy by dx or f dash of x, this is also a function of x. So for example, if you have say y is equal to sine of say 2x plus 1, then y dash is equal to 2 cos 2x plus 1. So obviously this is also a function of x, correct? So if this is f of x, then this is f dash of x, or you can call it g of x if you want, right? Normally we just write f dash of x, but I'm saying that the point is that this is by itself a function, just like this one is. Okay. Now if you have a function of x, you can evaluate that function at any point, at any value of x. So just like I can ask what is y of 0, y of 0 would be, here it will be, you put x equal to 0, so you get sine 2 0 plus 1, that's sine 1. Similarly, I can ask what is y dash of 0. So in that case, that will be, here you put x equal to 1, you get 2 cos 1, right? So we can ask for the value of the derivative at any point. That's given in this way. So another way to write this is, either I can write y dash of x naught, for example, is the value of the function y dash at x equal to x naught. Another notation, f dash of x naught. Okay. Or a different notation, if we are writing dy by dx instead of y dash, we can also write dy by dx at x equal to x naught. So if you see this notation, that means you're finding the derivative and putting x equal to x naught. So what is not notation for this is dy by dx naught. Okay, this is not a correct notation for this. Okay, this is not correct because here you are the meaning of this is you're differentiating y with respect to x naught, but x naught is a particular value, so you cannot differentiate anything with respect to a constant. So x naught is a constant, so here you cannot differentiate a function with respect to a constant or anything with respect to a constant. You can only differentiate it with respect to a variable. So this is not the correct notation. This dy by dx naught is not the correct notation at all. This is dy by dx at x equal to x naught. Okay, so this is just I'm just explaining the notation. There's no new concept as such. It's just a notation along with the recognition that y dash is also a function, just as y is a function. Now when we have implicit derivatives, so for example, x square plus y square equal to say 1, the circle, right? So here we found the derivative implicitly. We did not write y is equal to f of x and then differentiate. So in the previous class we saw that we differentiated like this implicitly. So 2x plus 2y dy by dx is equal to 0. So you get dy by dx is equal to minus x by y by taking over this and this to the other side, right? Okay, now in this case, also recall that this is not really a function, but two different functions. You can say multi-valued function, but multi-valued is by definition not a function, although sometimes we say it that way. So what we really mean when we say multi-valued function is it's actually two different functions given by the same equation. Okay. So this equation, if you plot x and all possible x and y values satisfying this equation, we know that we get this circle where this is 1, the radius is 1, right? We actually did this. We found the slope of the tangent at different points by using this, because dy by dx for any function is the slope of the tangent. So we did that. So what we were really doing is finding the value of dy by dx at different points. So just like here we wrote x equal to x naught, here you can write x equal to x naught, y equal to y naught, or xy equal to x naught, y naught, or just simply write the values of x and y. So for example, I can write 0, 1, right? X equal to 0, y equal to 1. That's the meaning. So if this is dy by dx, this minus x by y is dy by dx, then dy dx at 0, 1 is minus 0 by 1, which is 0. So we found this in the previous class. So the slope of the tangent here, I'm sorry, 0, 1. So this point, slope of the tangent here is 0. Similarly, dy dx at say, what's another point here? You can have 1 by root 2 comma 1 by root 2. Okay, that's another point. That will be here. Okay, this point will be 1 by root 2, 1 by root 2. Then at that point, what is the slope? Put 1 by root 2 for x and 1 by root 2 for y. So that will be equal to minus 1. And that's quite obvious from the diagram also, from the graph also, because this is the line. So this line is perpendicular to this line. This is y equal to x. So this one is at 45-degree angle, which is slope is 1. This is perpendicular to that, so its slope is minus 1. So that's obvious from the graph also. Similarly, you can find at any point. So if you substitute xy here, you will get the slope at that point. Okay. Now this notation is in a way error-free or foolproof, because once you substitute the value of x, the value of y is automatically determined such that it is a valid value of y obtained from this function. With this notation, the problem is you could, for example, evaluate this at say 2, 3 by writing 2, 3 here and writing substituting 2 and 3 here. You can evaluate dy by dx at 2, 3, but that's completely meaningless as far as this equation is concerned, because 2, 3 is not a point on this curve. So when using this notation, you just have to be careful. You can get values which are not really representing anything like the slope of the tangent, because you have taken some point which is not on the curve. Here, x value determines y value automatically by using the equation. So that danger is not there. Here you have to be careful with that. Anyway, that's not a problem. I just wanted you to understand this notation in case you see it. All right, so that's just a matter of notation. Now let's move on to higher order derivatives or successive differentiation. So again, we are not going to look at this in much detail. We just look at the definition. So the point is the same. You have y equal to f of x is a function, and therefore you can differentiate it to find y prime is equal to f prime of x. But this derivative is also a function. So you can ask what is a derivative of that function, and that's what we denote by y double prime or f double prime of x, or d square y by dx square, or d2y by dx square. Okay, this denotes what is called the second order derivative of y, second order derivative of y. Okay, and so once we talk about higher order derivatives, this thing is also called not just a derivative but first order derivative, right? Or let's write it here. This is called a first order derivative of y. So the second order derivative of y, what is the definition? I didn't define it. I just wrote the notation here. I told you the definition, but this is actually, so d square y by dx square actually denotes d dx of dy by dx, where dy by dx is a function of x. So you can differentiate it again with respect to x, and that's the notation. Okay. So in other words, the second order derivative of y is the first order derivative of the first order derivative of y. Okay, so if you take derivative twice, that is the second order derivative. That's just it, nothing more. So in a similar way, you can denote, you can define d to the n y dx to the n as the first order derivative of what? Of the n minus 1th order derivative, right? Correct? You can compare. Second order derivative is first order derivative of first order derivative. So normally we don't write d to the 1 y by dx to the 1, although that's fine. That's also a valid notation once you define this. We just don't write it. Just like we don't write x power 1, we just write x. So similarly here we write dy by dx, that is first order derivative. D square y by dx square is derivative of that. So nth order derivative must be first derivative of n minus 1th order derivative. So this is nth order derivative, or simply nth derivative. Okay, and this is the n minus 1th derivative inside the bracket. This. So the nth derivative is derivative of the n minus 1th derivative. So this is just a recursive formula for you to find any order derivative, because if you want to find, say, the 5th order derivative, you just differentiate the 4th derivative. But how do you find the 4th derivative? Differentiate the 3rd derivative. 3rd derivative is obtained by differentiating 2nd derivative, which is obtained by differentiating 1st derivative, and this you know how to find. So for example, y is equal to say x e to the power, or let's say x square e to the power x, and I can ask what is the 3rd order derivative. So first you differentiate it once, and by product rule, that is x square e to the power x. So I'm differentiating e power x first, plus derivative of x square, that is 2x e power x. Now second derivative, d square y by dx square. So now I have two terms here. Each should be differentiated using product rule again because both are products. So the first one again becomes x square e power x, because the same as before, plus 2x e power x. So this much is the first term. Okay, first term's derivative, I mean. And the second one's derivative is 2x e power x plus 2 e power x. Correct? Differentiate, forget the first term. Just taking the second term and differentiating, I get 2x derivative of e power x plus derivative of 2x, that's 2 e power x. Of course, this can be simplified because you see that the middle two terms are actually the same. Even if they are not the same, you will have a difference of a constant possibly, but they'll almost be the same. So here you can write 4x e power x plus 2 e power x. Okay, this is just the second derivative. Now to get the third derivative, you have to differentiate this again. So again, the first term, we have differentiated it already. So it's the same thing. Second one is very similar to this thing, only that 4 instead of 2. So that will be 4x e to the x plus 4 e to the x. Okay. And this will be just 2 e to the x. Again, this is actually the answer, but you can simplify it a little bit by noticing that these are common, right? These terms are common. So that'll give you 6x e to the power x. So as I said, constant can be different. And similarly, these two are actually the same term with different constants. So you get 6 e to the x. This is the third derivative of this function. Other notations for this y3 like this, I mean, or y triple dash, right? Or this y3 of x, or just y3. So here also, this is also denoted by yn in brackets, not y to the power n. This is y raised to the power n. This is not that. This is nth derivative of y. This is a common notation for nth derivative of y. Okay, in brackets, you have to write the number in brackets, or you can put n dashes here like this, but that's obviously tedious for more than 3. So normally after 3 you don't go on writing. In fact, there is another notation where for the fourth derivative, for example, you write Roman numerals here. So y, this is fourth derivative. Okay, but the other notation is definitely preferable. This is definitely preferable, much clearer. Okay, so that's higher derivatives. So you can think of what would happen if you find, you take say something like sine of ax and you differentiate this n times. What should happen? Let's start with sine x to make it simpler. What is the first derivative? We know that it is cos x. Now, what is the second derivative? That's the derivative of cos x, which is minus sine x. One second. You're asking me to explain the third step. Third step meaning this one, the third derivative. Okay. So it's just repeated differentiation. So this higher order derivatives is also called successive differentiation or repeated differentiation. So you don't actually have to think of it as higher derivatives. You just think of it as differentiating again and again. So you start with the given function. Here that is x square e to the power x. Then differentiate that to get this. This is just product rule. Now differentiate it again. But when you're differentiating, so forget that it's the derivative of this function. Just consider this as a function all by itself and think of how will you differentiate it. Well, you have two terms here. Each term is a product. So you will apply product rule to obtain x square e to the x, right? X square e to the x plus 2x e to the power x. Then differentiating this, you get 2x e to the power x, differentiating e power x, plus differentiating 2x, you get 2 e power x. Only thing is, uh, these two terms, the second and third terms, are the same. So you can combine them and write 4x e power x here. So this is the second derivative, x square e power x plus 4x e power x plus 2 e power x. Now, to get the third derivative, again, don't think of it as higher order differentiation, just differentiate this function once. So if you differentiate this once, what do you get? You have here x square e power x. When you differentiate that, what do you get? X square derivative of e power x, which is e power x itself, plus 2x, that is derivative of x square, which is 2x e power x. Okay, that's the first term here, this one. Similarly, 4x e power x. How do you differentiate that? Product rule again. So 4x derivative of e power x, which is e power x, plus derivative of 4x, which is 4 e power x. And that's the second term here. Third term is 2 e power x, whose derivative is just 2 e power x. Then you can combine, because this and this are again the same, except you have 2 here and 4 here. But that's just adding up to 6. So 6 x e power x. Similarly, here you have 4 e power x, and here you have 2 e power x, which add up to give 6 e power x. Is that clear, or you have some other question about this? Something else in this which you didn't understand? Okay, fine. So moving on, we have y equal to sine x. Its first derivative is cos x. Now to obtain the second derivative of y, merely differentiate this again as a function on its own. So cos x derivative is minus sine x, we know this. Now it's almost as if we have gotten back to the first function, except there's a minus sign. Now if you find third derivative, okay, so I'll switch to the other notation, y3. This is minus is already there, and sin x, when you differentiate, you get cos x. The minus doesn't go away. The minus is not coming from the differentiation, it's already there. When you differentiate sin x, you get cos x. And if you differentiate that again, what happens? Cos x derivative is minus sin x, right? But there is already a minus here. So you get minus of minus sin x, which is plus sin x, which is actually equal to y itself, right? So what happens if you differentiate n times? In general, what will be yn? Depends on the value of n. Clear? If so I'll tell you what the cases are, and then you can figure out what the values will be. So if n is 0 or 4 or 8 or any multiple of 4, then it will be, in fact, I'll tell you what it will be. It will be sin x itself. So firstly, what is zeroth derivative? Remember, the idea here is nth derivative represents n differentiations, n successive differentiations. So if n is 0, we get what is called the zeroth derivative. But what is the meaning of that? It means you differentiate 0 times. So if you differentiate 0 times, that means you're not differentiated at all. So yes, that is the function itself. So the zeroth derivative is y itself, okay, or this is y itself. Remember again, it's not y power 0. Y power 0 would be 1. This is 0th order differentiation of y, which is y itself. Okay, so this is saying if you differentiate 0 times, this function will remain sin x. If you differentiate 4 times, you will get sin x again. If you differentiate 8 times, then also you will get sin x. So you can think of why that is so. Okay, so what are the other cases here? You will have n equal to 1, 5, 9, etc. That is, instead of 0, 4, 8, you just add 1 to each. So 1, 5, 9. So the first derivative, the fifth derivative, the ninth derivative, and so on. So what will those be? Then similarly, second, sixth, 10th, and so on. And third, 7th, 11th, and so on. So there are 4 possible values of these derivatives, and that's all. Okay, so you can think of this, and then do the same thing with sine of ax, where a is a constant. Okay, so for a constant, find what is yn in the same way. Similarly, you can try y equal to cos ax and e power ax. So e power ax is actually the simplest one of these. So try that. Other functions are maybe a little more difficult, but still you can take something like x power n and do it. So x power n, or let's say x power k, and you can find its nth derivative for general value of k, general value of n, where k is also some positive integer.